Ever wondered how cutting-edge AI generates those incredibly realistic images you see online?
It's pretty amazing stuff.
Yeah, and it goes beyond just learning what things look like, doesn't it? It seems like it's more about understanding their deepest structural rules.
Exactly, like knowing the recipe, not just seeing the finished cake.
Right. Imagine an AI that doesn't just, draw a tree, but actually knows how to grow one, sort of branch by tiny branch.
That's a great way to put it.
So today's deep dive is into hybrid neurofractal models. It's this really groundbreaking field merging, the mathematical elegance of nature's patterns with modern neural networks.
Mm-hmm.
Our mission really is to give you a shortcut to understanding how this new approach is transforming how we generate and maybe even understand complex data. Think natural forms, synthetic images, that kind of thing.
And what's truly fascinating here, I think, is this isn't just about pixel values on a screen. It's about the AI learning the very composition of complexity itself, how things are put together.
Okay, let's unpack that a bit. To really get this, we probably need to touch on fractal geometry first, right?
Definitely. That's the foundation.
Pioneered by Benoit Mandelbrot. Fractals give us the language to describe all those irregular, self-repeating patterns we see everywhere in nature.
Coastlines, clouds.
Even the branching in our lungs, yeah. Unlike, simple squares or circles, fractals embrace this idea of roughness.
And fractional dimensions, which sounds weird but makes sense visually.
Yeah, like the Sierpieski triangle. It's not quite 1D, not quite 2D. It's somewhere in between, right? Around 1.585, I think.
That's the one. Beautifully complex, all from repeating a simple rule.
And those rules often come from something called iterated function systems, or IFSs.
Exactly. They're basically just concise sets of rules. Simple transformations, scaling, rotating, shifting, applied over and over again. Recursively.
Like the instructions for building Barnsley's fern, which looks incredibly organic.
It does. It's stunning what simple recursive rules can generate.
Okay, so generating is, relatively speaking, straightforward if you have the rules. But here's the kicker, the inverse problem.
Ah, yes.
What if you just see a picture of that fern and you want to figure out the exact rules that made it?
That's the challenge. That's the inverse problem of fractal construction.
And you mentioned earlier, this is where things get really tricky computationally.
Extremely tricky. It's NP hard.
NP hard, meaning what exactly for practical purposes?
It means that for any classical sort of deterministic computer algorithm, finding the optimal set of those IFS rules just from looking at the image, it's practically impossible if the fractal is complex. The search space is just too vast.
So, like trying to guess the exact tiny seed and growth conditions just by looking at a fully grown, massive oak tree.
That's a pretty good analogy, yeah. You hit a computational wall.
Yeah.
And this barrier, this intractability, is really the core justification for needing a different approach, like a neural network approach.
Right. So if classical methods hit this wall, this is where deep neural networks come in. They offer a different way.
They do. A fundamentally different way. Deep neural networks are powerful probabilistic generators.
Probabilistic, meaning they deal in likelihoods, not certainties.
Precisely. Instead of finding one exact set of rules, they learn to capture the whole underlying probability distribution of the data. What kinds of rules are likely to produce something like this?
Okay. And they do this using something called a latent space.
Yes, the latent space. You can think of it as a kind of compressed, abstract map learned from the data.
A map where similar things are grouped together.
Exactly. It captures the most important features, the essence, in a lower dimensional space, like a really well-organized mental library.
And this structure allows for cool things, like smoothly morphing between faces, latent space interpolation.
Or even that vector arithmetic people talk about. King minus man plus woman equals queen, or the smiling woman example.
Smiling woman minus neutral woman plus neutral man equals smiling man. It sounds like magic.
It feels a bit like it, but it shows the space has learned meaningful relationships.
Okay, which brings us right to the core. Hybrid neurofractal models. You're saying the idea is to actually embed those fractal principles, recursion, self-similarity, directly into the neural network's architecture.
That's the breakthrough, yes. Embedding them as fundamental design choices or architectural priors.
So the network is sort of pre-wired to think fractally?
In a sense, the fractal generative model by Lee and colleagues is a great example. It breaks down the whole generation task into these recursive, sort of atomic neural modules.
Atomic, like little self-contained units.
Yeah, and they generate the image piece by piece, pixel by pixel almost, using a hierarchical divide-and-conquer strategy. Like building with Legos, but the Legos are smart neural nets.
That sounds incredibly efficient compared to models that look at the whole image at once.
Oh, it is. Hugely efficient.
Yeah.
Because it uses localized attention at each level of this hierarchy.
Meaning it only focuses on the relevant bits nearby.
Exactly. For a 256 by 256 image, its attention mechanism is something like 4096 times faster than a traditional flat autoregressive model that has to consider every single previous pixel.
Wow, 40 and 96 times. That's a massive difference.
It really is. It scales so much better.
So connecting this back to the tree analogy, this kind of model isn't just learning what a tree looks like at the pixel level.
No. It's learning the recursive generative process. It's learning, in essence, how to grow a tree, computationally speaking.
It's learning the structural rules of composition, the grammar of the image, not just the vocabulary.
Beautifully put. It's learning the underlying generative logic.
So wrapping up then, from Mandelbrot's descriptions of nature's roughness to these hybrid models generating complex data with incredible efficiency, it feels like a major leap.
It is. It really changes how AI can potentially build and understand complex, structured information.
And it raises some deep questions too, doesn't it?
Absolutely. If AI can learn to grow data, learn form in this really fundamental way, what does that imply about our own understanding of creativity, or even the nature of form itself?
That's a big question to ponder. And of course, with powerful models like these, responsibility comes into play, thinking about ethical considerations.
Crucial. Things like data privacy, potential biases in how they learn, copyright for generated content. It all needs careful thought.
Making sure this new frontier is not just innovative, but also accessible, verifiable, and trustworthy for everyone. It really challenges our perceptions, doesn't it? If an AI can invent realities indistinguishable from natural ones, how do we navigate that?
A profound consideration indeed. Lots to think about.